Now let me introduce a friend that I've worked with for 25 years. I've spent a good fraction of my career trying to come up with computers to let John Etgen do things that had never been done before, to break through some computational problems, some scientific problems, and do fun things. And John, thank you very much, not only for today, but for the chance to work with you.
Thanks, Keith. That's very gracious. Probably more gracious than I deserve. There's a fair chance that in 35 minutes from now, you're going to conclude that I'm a crazy person. And actually, I probably am. I'm getting to the point in my technical career now where I'm not actually good for doing any real work anymore. But there is one thing that time and experience affords you a perspective on, and that is, how are things really going, right? Are we really getting there? Are we really making it? So a good friend and mentor of mine once said, never give a talk that has any more than 1.5 ideas. So I actually do have kind of 1.5 ideas in the talk, but it's not going to go like a normal technical presentation. I'm not going to stand up here and kind of walk you through some great thing that BP is doing or some piece of mathematics or computational physics. Actually, I think I'm going to show almost none of that. What I'm going to try to do is tickle your complacency a bit, right? I mean, I think this space, scientific computing, it is scientific computing, like even in energy, right? But let's talk scientific computing as a whole. Feel a little stale to me, right? So I chose this title to be provocative because I think the answer is no. Like not just no, I mean like not even close, like not even the same ballpark, not even the same game, not the same sport. I mean, it just, forget it. We are actually crumbling, right? Scientific computing, numerical physics, things like that, it's going down the drain. And if we don't change something about what we're doing, it is going to go down the drain. It's a bit ironic that we're having the meeting in a biosciences building because the most ambitious person I ever met was, a synthetic genomist, right? I mean, he was doing synthetic genomics, basically. His ambitions were bigger than ours. Our ambition is, let's do a numerical simulation that makes an image of the subsurface, or let's do a fluid flow for carbon capture and sequestration. No, this guy wanted to capture the entire galaxy within about 150,000 years. And he had a plan to do it. He was a real crazy person. The question is, do we need crazy people or not? Well, you'll see what my opinion on that ultimately is. Okay, so the title of the talk is, are we approaching a singularity? Before I kind of define that term, before we kind of get rolling into that, I just want to say a few things about me. So, who am I? What do I want? You'll hear me use that question maybe a couple more times. I'm not a mathematician, but I'm passable enough at mathematics that I can use it. I'm certainly not a computer scientist, right? However, I'm passable enough at that stuff that I can combine mathematics and a bit of computer science and produce something that, strangely enough, for the last 30 years, people would pay actually a non-trivial salary to somebody to do, right? So that's that picture you see up there. Image of the subsurface, that's what the oil and gas business used to do anyway. It's what we used to consider to be the fun, glamorous stuff. Maybe it's still somewhat fun and glamorous. Actually, who am I? What do I want? I mean, yes, I like powering civilization. That's all good, right? And I'm going to set the whole climate change thing aside. You saw it, no disclaimer at all. This is my opinion. This is not my company's opinion at all. I don't really care. I like pictures of the subsurface, right? I mean, I'm not in the oil well drilling part of the business. I mean, I like it when the company makes money. That's good stuff, right? Because that pays my salary. But fundamentally, I like using mathematics, physics, computation to see things that people hadn't seen before. Right? So I'll tell you a little bit more about myself a little later on, but that's me. That's what I do. At the end of the end, who am I? What do I want? I want to do that kind of stuff. At least I used to want to. Okay. I can count, probably on one hand, the number of times in technical computing that I got a real adrenaline rush. Probably less than 5, right? I'll tell you the first one. I was taking a class in Fortran in high school. And we did all the basic stuff about language and syntax and all that stuff. We got to the end where we were going to do something sophisticated and fun and challenging. And that was, which was pretty tricky to lay out on high school students in the 1970s, was the instructor was going to teach us the difference between an n squared sort and a log n sort. Right? So we had to actually take notes in class and code up quicksort. Right? Now, nowadays, that's just like boring, basic stuff. Maybe none of you actually know how to do it, but it's not a trivial algorithm to code up, to get right and debug it. But so we coded up, got it all working, got it to compile, and then the first thing we did is on a really crummy computer that had iron donut core memory, in fact. We ran the n squared sort on 15,000 integers, right? Random 15,000 integers. The machine only had like 48K of memory, so the input and the output and the program just about filled everything. It ran for 45 minutes with an n squared sort, right? This was a slow machine, right? Then, okay, run your quicksort algorithm. Ran in 15 seconds. Whoa, holy crap, right? I learned that a good algorithm beats a fast computer every day of the week, right? First lesson, actually, that you probably should learn. You should learn it that way. The second adrenaline rush was actually the exact opposite, which was, now I've graduated from high school, I went to Colorado School of Mines. They actually had a fairly first-class computer center. It was a computer center in those days. And so actually, I wasn't yet in a computer science class, but I took my old codes from high school and I said, well, let's see how fast they run on the School of Mines machine. So I compiled them and ran them, and guess what happened? Well, they both ran. Both the n squared sort and the quicksort ran in about 15 milliseconds, right? I mean, there was no difference, actually. You could not distinguish the speed at which that machine could sort 15,000 integers because it was so fast that it didn't matter. So that's where I learned the second lesson of computing, which is a fast computer beats a good algorithm every day. All right, so probably the next adrenaline rush was when I actually got my first professional job, went to work for Amoco in Tulsa, and I got access to a Cray 2. That was a damn nice machine. Right? That was really kick-ass machine in the day. Then all the stuff I was doing in graduate school, which, I mean, I'll show you the machine. I should not show you a picture. I'll describe the machine we had in college, in graduate school. It was a pretty damn good machine, but the Cray 2 was a really nice machine. That was like, wow, look at what you can do. So that's probably number 3. Number 4 was not that long after that, where I got access to, now I realize that some of you who know me are going like, oh God, he's gonna bring up that damn connection machine. Yes, I'm gonna bring up that damn connection machine. I got access to a CM2, which was a piece of junk hardware-wise, right? It was a very, very different paradigm. And I coded up, much easier to code up, actually. The code for the connection machine was about 10 times shorter than the code for the Cray 2. And it ran about 20 times faster than the Cray 2. Whoa, holy crap, they're on to something. All right, so I've not had one since. For all of the good work that Keith Gray did through the years, and he did exactly what he said, which was he tried to keep me entertained, and not just me, but our entire group of subsurface scientists and reservoir engineers, geophysicists, et cetera, busy, happy with computing, and he did. He did a fantastic job at that. There was never again a moment like, wow, that's really if you'll pardon the language, a kick-ass advance. It just didn't happen. Okay, so what's a singularity? Well, anybody read Kurzweil's book? I actually haven't read the book, right? I've heard people like him talk. This is the idea that even after you normalize out any possible exponential, growth is still exponentially fast, or better, right? Things are just improving at such a rapid rate that the future comes so quickly and is so transformative that the past is almost unrecognizable, right? So are we headed for something like that? Now, I mean, you know about Moore's law, right? Moore's law is an exponential. That says we're on some kind of exponential trajectory. How you feeling about Moore's law these days? Right? Well, but actually, we could normalize that out, right? A singularity does not happen via Moore's law. We have to do better than Moore's law. Are we, is kind of the fundamental question. If not, is it worth even asking? Why not? More importantly, is anybody going to do anything about it? That's my whole mission today. One of you, maybe one of you, if I'm lucky, out there in the virtual audience too, maybe, one of you will be the person that makes it possible that we get on a trajectory better than exponential. However, if we just keep doing our normal day jobs, that includes me too, not going to happen. Okay. Do you know what a singularity would look like? Well, probably our best model is the Industrial Revolution. So roughly, human civilization went from riding horses to putting robots on Mars in 100 years, right? I'm using big O kind of arithmetic, right? So maybe it's 150 or 200 years, whatever. Human population went from subsistence farming or something like that, not large-scale agriculture, but small-scale agriculture, to basically everybody working in pretty specialized roles, right, over that course of time. More transition happened in the last 100 years than all of planetary history. Another thing worth noting is things went from being highly custom-made to basically just massively produced, right? I mean, you can see that, obviously, the semiconductor manufacturing world is part of that. Here's one that I think is important. If you were going to survive in the late 1700s, early 1800s, you kind of had to be good at almost everything, right? You had to know to plant a crop. You had to know how to harvest that crop. You had to process that crop. You had to know how to raise animals. You probably had to know how to build your own house. You had to know how to dig a well. You had to know how to melt down fat to create a candle so you had light at night. I mean, you had to know how to do everything to ensure your survival. What I would guess is, no, we don't know how to do that anymore, right? We're all highly, highly specialized. You can decide whether that's a good or a bad thing, but in fact, the Industrial Revolution forced us to have to specialize because we are finite, we're limited. As technology explodes super exponentially, you have no choice but to concentrate down so that you can compete, right? So you become highly specialized. The Industrial Revolution is nothing more than machines that make machines that make machines that make machines that make machines. The computational equivalent of that would be software that writes software that writes software that writes software. Well, we do have compilers. That's software that writes software. We have some of the new modern AI kind of languages and constructs. That's kind of software that writes software, maybe that writes software, maybe two or three levels deep. Is it going deep enough? So there's another interesting phenomenon I'd say about singularities, which I think is a very human thing. It's what I call retrotech, which is the vast power and intelligence of a civilization to create interchangeable parts that can be used under a wide variety of maybe even unknown or unpredicted applications, is often used to make applications that are lower tech than the technology that made the parts. So here's my little picture of that. So there's a 1/4-20 machine screw, pan head machine screw. Well, that's an integral part of that rocket vehicle that you see there. I built that rocket vehicle. But that rocket vehicle is actually not high tech. I mean, it's using a bit of 18th century chemistry, some 1930s level metallurgy, but it has a bunch of those 1/4-20 screws in it. Those were made in a very sophisticated factory. Right? The factory is infinitely more technically advanced than that stupid rocket that I built that launched. Now that looks fun, it looks romantic, and it's cool, and it goes fast, and all that fun stuff. But it's an example of retrotech. I built something simple, primitive, handmade out of what civilization produced, which is the ability to produce essentially all the 1/4-20 screws the world will ever need at zero cost. Right? I mean, yeah, when you go buy them at the hardware store, they cost 2 cents or something. But effectively, they're zero cost to manufacture. Okay. Let's return to scientific computing now, which is what you want to hear about. Well, can we say that we're maybe already in it, right? So in 1985, I had access to a convex C1. Those of you younger than me are like, what the hell is that? Never heard of that. Those of you who are my age or older, you probably do remember what it was. It could do about 25 megaflops. The tagline was a quarter of a cray at a tenth the cost. And it kind of was. It kind of did do that. So the cluster that I currently have access to, I don't see Elizabeth. I see Elizabeth there, so she'll yell at me if I got the number slightly wrong. Just within a reasonable approximation, it does about 25 times 10 to the 15th floating point operations per second when it's all humming together. So in 37 years, because that's the time span if I calculated correctly, a factor of 10 to the 9th in computing power available to me as a person. That's pretty impressive, right? Wow. That took 37 years for that to all happen. The analogy would be if I had a device that was capable of transporting a piece of material at 1 meter per second in 1985, it could now transport that piece of material faster than the speed of light. Right? That would be the analogy. Right? Holy crap, that's a lot. But what I would claim is, well, wait a minute, not so fast. Right? The reality isn't quite as good as that initial wow factor. All right, so reiterate my fundamental premise. Actually, I don't think we're in a singularity. I think actually we're kind of plateauing, right? It's making diminishing rates of progress as time goes on, not accelerating rates of progress. I think there are some positive signs, though, but I'm also kind of pessimistic. So we'll talk about both of those things. What are the positive signs? Why am I pessimistic? All right, so that convex was a single computational instance, right? It wasn't a cluster. It was a vector machine, kind of patterned after kind of lower cost silicon after what the Cray architecture was. The cluster that I'm using is, again, Elizabeth will yell at me if I have the number slightly wrong, somewhere between 10 to the 4th and 10 to the 5th instances. Okay, so if I normalize by price also, because actually the cluster probably costs about 10 times fair retail price is what that convex cost. We've only really seen about a 10 to the 3rd to 10 to the 4th, depending on how you do the math, improvement in single instance speed, right, in 37 years. Okay, that could still be on an exponential trajectory. I mean, it might not necessarily be bad. So, how did that happen, right? Now, one good thing is they did figure out how to make it cheaper, right? Because a lot of the advantage came because I just bought a lot more instances, right? So in some sense, maybe I don't care, maybe it's fine, maybe the fact that there's a lot more instances is okay, but it actually forces us into a model of thinking about how to do scientific computing that, well, may not have all the properties that we want. Simple question. All right. So what would we think we would see if we were in this singularity or in the process of it happening? Well, I think for one thing, you'd see an exploding diversity of applications. I don't know, I guess I'll reflect that question to you guys. Do you feel like we're seeing an exploding diversity of applications? In computational fluid dynamics, I think the answer is no. In computational seismology, the answer is definitely no. In reservoir engineering, I think the answer is no. Maybe there's some other scientific fields that actually are having exploding diversity of applications in scientific computing, but it's kind of iffy. Not sure I see that one. Here's one that I think we're definitely not seeing. Human beings are not becoming increasingly more specialized, right? The range of skills and tools you need to know to be effective and to get a job or to get your degree or whatever it is, that range is remaining just as wide. That fights against an industrial revolution-like phenomenon. That fights against the singularity. So, in my company, if I was standing up here, recruiting for my company and following the actual company line, I'd be saying, oh no, you need to cross-skill, you need to be, multi-talented, multidisciplinary, all that stuff. That's the fastest way to kill an industrial revolution-like phenomenon there is. Let people specialize. This is my personal opinion. You want industrial revolution-like, singularity-like behavior? Let people hyper-specialize. What do you hear in society? No, everybody's got to be a generalist. Okay, we're trying to live back in the 1800s again. After they shut down the electric grid, we might be. I didn't say that. So another more important factor is creating complex objects should get easier. Right? If you look at the variety of things that are manufactured, let's take an example of rubber duckies. Right? We can make rubber duckies in a big factory now, right? That's actually a pretty complicated little thing to make. If I told you go home and make a rubber ducky, well, unless you had a bar of soap and a pocket knife to make a soap ducky, it would be impossible for you to make it, right? However, we can churn out rubber duckies by the millions, right? It gets easier to produce complicated objects. Now, look at the computers that we're building now. Those things are pretty damn complicated objects, and we're churning them out by the millions. It's actually easy to manufacture that stuff. We see some of that on the hardware side. How's it going on the software side? Right? Is it getting easier to create complicated pieces of software? Well, there is one area, which I'm going to come to in a second, after I do the next thing, where I think that is true. So actually, I think those people are onto the right mentality. I claim this notion of retrotech would become evident if we were in a singularity. You'd have people using the immense industrial revolution capacity in computing to do really dumb basic things. All right, well, in that lower corner there is a picture of a seismic recording system that I built for about $5. Now, somewhere in, I don't know, China, Taiwan, Malaysia, I don't know, there's several different semiconductor factories that make op amps, they make little ARM CPUs, they make all sorts of other electronic components that I can buy for a penny each, or pretty close, not quite. And because I can go on the Arduino website and download from GitHub kind of the pieces I need to put the device drivers together, put all that stuff together, go into an IDE, and build myself something that very, very skilled scientists were paid a lot of money to build in like the 1960s and 1970s. Right? The capability that I built isn't any better than what was available in the 1960s. Just, I can build it myself on my kitchen table for a few dollars a part. That's Retrotech at work again. So again, the semiconductor industry kind of has some of the properties. But are they spilling over into scientific computing? It doesn't seem like they are as much as I would like. All right, here's the most hopeful sign. So for the next, well, it's another 6 or 7 months to go, I have the privilege, and it is a genuine privilege, to edit a medium important scientific journal. It's a journal, Geophysics, right? It's the premier journal of applied geophysics. That would be the SEG's tagline. I'm the editor of that, which means I read every single paper we publish. And you know what I'm seeing? UNet is taking over the damn world. Right? I mean, not every paper, but a large fraction of the papers basically are copying this idea. And they're doing things with it that I'm sure the authors that invented that method had no idea that somebody would ever do that thing with their invention, but they are. Yeah, the AI guys kind of get it, I think, actually. If you're just going to go pure AI, they kind of got the message, which is build tools that build tools that build tools that build tools, multiple levels of hierarchy. You can become highly specialized in what you do. You don't need to know everything else, because actually all the software is pretty transportable, pretty easy to learn, easy to do your little piece, and then live on top of the foundation of whatever everybody else built. Right? The AI guys get it. But if you're like a hardcore computational physicist, you don't get it, actually. You're not doing that. I don't see that behavior. Well, unless you're using UNet to replace numerical physics, which I hate, frankly. Doesn't mean it's not right. I mean, we'll come to more about me in a second. It's not clear that I like that, but maybe they're onto something. Okay, so back in Tulsa, more senior scientist than me, very good scientist. Very few of you will know his name. Highly unlikely that he's watching this. If he is, hi Richard, how's it going? I hope it's going better than it used to go. He had a law, and it was everything rots. Right? Simply stated, everything rots. If you leave your food in the refrigerator long enough, it rots. Leave your car in the driveway, it rots. Don't reboot your Windows computer, it rots. It's actually not supposed to happen in computing. Computing's supposed to be, forget the AI stuff for a second. It's supposed to be deterministic, right? If I run a seismic simulation twice, I kind of want the same answer. with all the same input, same code, same everything. I kind of want the same answer twice. It's becoming less clear that you will get it. So it's not Siegel's law should not apply in computing, but it seems to. Some of that is related to what I would claim are bad decisions. They were expedient in the moment. Bill Joy used to think we'll never have enough disk space to store executables because executables are getting big, because they're getting complicated, because the microprocessors are getting complicated, so we better save the world from itself and not let people statically link codes anymore. Oh, God. That was like, to me, that was the biggest crime ever perpetrated in technical computing. I don't know how much this matters, right? I'm still pondering that one. So you can disagree with me if you like and tell me, no, dynamic linking is actually great. Okay, maybe it is. I don't believe it, though. All right. So the easiest logical model of computing is this. You got some inputs, you got a really fast CPU, and you make your outputs. All right, all's well and good. That was the convex, basically, and the original Cray machines. Well, of course, you tumble pretty quickly to this idea. If I got a bunch of inputs that are all subdivisible, right? They're all going to be processed independently to make their independent outputs, which are then combined in some way, shape, or form. Well, I can actually do just about as good, maybe even better, with a handful of pretty fast CPUs. Okay, cool. This is the first thing that Keith kind of did for me when I moved off of the connection machine to, actually I think it was a cluster of SGI boxes. Right? And maybe he actually gave me 4, in fact, so that's why I drew the diagram that way. No, actually maybe it was 8, so I drew a factor of 2 too few. Well, actually we've taken that paradigm, well, to about 10 to the 4th to 10 to the 5th instances now, right? Actually, I was an idiot. I used to claim that the level of job-level parallelism that we could tolerate was about as many fingers as you have on your hand, so order of 10. Because I can't keep track of 10 to the 4th things all going on at once in my head. There's too many things. I don't have that many fingers. I can't count them, right? No, actually, human beings seem to have about 10 to the 4th logical fingers. Not physical fingers, logical fingers, because they seem to be able to count that high. You got to decide if that actually continues forever, right? Could you build a singularity out of this by just expanding the number of parallel instances ad infinitum, not just at a doubling every year or whatever rate, but at a accelerating faster than exponential rate? I kind of doubt it. I think there's a limit to how far we can scale this model. Notice I didn't put any communication connections between them. As soon as you require these things to communicate with each other, it gets a lot hairier. All right, well, actually, when you look at the hardware, that's not how high-performance computing is really done down on the metal. The way it's done is something called a pipeline, right? What you realize is you can't actually add 2 floating point numbers in one clock cycle. Not really. Not if you just have 2 floating point numbers and a little arithmetic unit. It actually takes several clocks to do it. And yeah, it's really horrifying to see how hard it is to do a divide, right? So what you do is you build a pipeline. I won't read the quote at the bottom, but it was quoted to me by an instructor of Cray assembler language, right? And he was explaining how the Cray works, how it gets one combination of a read, an add, a multiply, and a memory write in one clock cycle. And it gets it by building pipelines, right? So those of you who are kind of down in the deep hardware stuff, you're actually thinking this way. Just to let you know that I knew about that stuff. All right, so I'm going to ask this question. I don't know how important it is. I think actually I'm going to try to convince you it's not important, but I miss it. All right, you know the song, "Where Have All the Cowboys Gone?" Right? Where are all the big personalities in scientific computing? I mean, if one of you are it, or some of you are them, I don't know who you are, right? These two people changed our world, right? I don't see many people, crazy lunatics, right? Did any of you, raise your hands if you know, did you personally know Seymour Cray? Have you ever met Seymour Cray? Anybody in this room? No. Ah, okay, a few, good, fantastic. All right, so I want to ask you if the following thing is true. I never met him. Rumor had it that in addition to the fantastic things he did in computing, every year he would build a wooden sailboat. I mean, like a large one, like that you could sail in. And then, don't know if he did anything with it, he would burn it to the ground. And he would do that every year. Is there any truth to that rumor? I heard it from a well-placed source. Right? Yeah, it's true? Yeah, fantastic. Okay, he was a cowboy. Or whatever, a radical. He was going to change the world. And he did change the world. Do you know the second individual, Danny Hillis? He was also pretty radical. He invented the connection machine. It was his PhD project at MIT, right? This was a PhD thesis. This is a pretty good PhD thesis, actually, right? I think he earned his degree. He showed you that adapting computing to the model of the physics might be a useful paradigm. That's what the connection machine enabled you to do, was to write the program in a way that the computer looked like the physics you were trying to do. That was the idea, right? Very interesting idea. Some very smart people worked for him. A couple of my friends worked for him for a number of years. I mean, do you know what he's doing now? Do you know his project now is to build the millennium clock? He's basically out in the desert building a clock that'll run for 10,000 years out of rocks because he thinks civilization is going to end and the future intelligent beings on this planet won't know what time it is. Right? So, interesting individual. All right, so this is an example of Siegel's law because actually what I tried to highlight to you ended up in the wrong frickin' box because PowerPoint sabotaged me. Who are we? What do we want? So I fly to London, well, not in the last 2 years, but I used to fly to London a lot. And I'm not an early morning person. So when you get off the plane in London, it's like 3 a.m. Houston time. And I'm devastated. I don't know who I am. I don't know why I'm there. I feel sick. I just want to go back to bed. But I have to fill out, you don't anymore, actually, they got rid of this. You had to fill out this landing card thing. And in that landing card, it says occupation. Who are you? Right? And I found that writing my BP title, that was a bad idea because I would mess it up. And they'd actually quiz me, like, wait a minute, do you work for BP? Can you prove it? Where's your company badge? Oh, crap, I don't know. So I found the most truthful thing I could say, and the one that I could actually remember, because it was true at 3 a.m. when I was unconscious, was scientist. Right? That's what I do. I think I'm a scientist. Here's the problem. I don't think scientists are the key to a singularity in scientific computing. I think they're a component, right? People like Danny Hillis, people like Seymour Cray. Yeah, I mean, they're useful, they're necessary, they spark all sorts of things. They don't actually make the singularity happen. All right, I think there's 3 kinds of people. And I put a little dot for kind of where I am. Scientists who pursue knowledge. artists who pursue beauty and engineers that pursue value. Now, my company is probably going to fire me if they see this presentation, because they think I'm probably way down in that corner down there, right? Pursuing value, that's what you're supposed to be doing. Well, in a very long wavelength sense, my presentation today is in pursuit of some value. But actually, me personally, no, it just doesn't excite me. A little bit of beauty does, a piece of code that really looks cool, that's really expressed in a clever way, it really runs fast, you're really happy with it, that's art, that's the artist in you, right? The scientist wouldn't care. The scientist would just know is, I had a hypothesis that this would work this way, I set up a test which should prove or disprove that hypothesis, and I succeeded in proving or disproving the hypothesis. That's all the scientists would care. They would not care whether the code was cool, whether it's really fast. They would just care whether they gain the knowledge or not, right? Now, I have some artist in me, because I am also amenable to that, ooh, that code was pretty cool. My experiences with, quicksort and stuff like that, that's the artist in you coming out, if you had similar things. If my story to you was like totally dry, like, well, of course, that's a testable hypothesis, there's nothing interesting in that conclusion. Okay, there's not much artist in you, at least not on that topic. All right? But if you went, oh yeah, I remember doing that too, that was cool. Okay, there's some artist in you. Which is a good thing, we need artists. All right, so I would claim in some ways art predicts real life in our behavior in this space. So do you know the legend of John Henry? You probably have to be my age or older to remember. Okay, so basically at the Industrial Revolution, beginning of the Industrial Revolution, a gentleman had invented a steam-powered drill for drilling railroad tunnels. And he was trying to sell it. Now, the state of the art at the time was you had some big guys with hammers and long chisels, and they would drill the holes to set the charges by hand hammering the dynamite holes. And there was one guy named John Henry. It purported to actually be a real person, although depending on how you research this, you'll see maybe there's some disagreement on that. But anyway, there's a folk song about this. He was the best. And so when the steam-powered drill guy came to sell his wares, they said, well, I'll tell you what, we're not going to buy that unless you can beat our John Henry guy here, right? Because crap, John Henry, if he can drill holes faster than your newfangled steam-powered drill, we got no use for you, right? We'll just get our John Henrys. So they had a race. Well, who do you think won? Well, so you would think, I'm talking Industrial Revolution, and obviously mechanized power can vastly exceed what humans can do. No, that's not what happened. It was a fairly early prototype of the steam drill, and John Henry was damn good at what he did. He won. He beat the machine. Now, there's only one problem, depending on how you kind of interpret the folktale. Basically, it caused him to have an aortic aneurysm, and he dropped dead after the race, right? So it killed him to win, but he won. We face exactly that same John Henry danger in what we're doing, which is, well, there's a friend of mine, Fatmir Hoxha, who's sitting right there. And if you, let's have a race between somebody who has an automated code for writing a finite difference stencil, right? So they've got a machine that builds a machine that builds a machine. And we're going to have a race, and we're going to see who writes a faster finite difference code, the machine that builds the machine that builds the machine, or Fatmir. Actually, right now, I think Fatmir might win. Now, he's going to be like drinking 50 coffees and working 24 hours a day, and he's going to be freaking out, sweating bullets, but he probably will win. We're at that John Henry phase. But now, of course, this is just a folk legend, right? I mean, of course, we know who ultimately wins this race. The machines that build the machines that build the machines ultimately just mow over what humans can do, right? And they have to. The problem is, as people, we're tempted to root for John Henry. All right, so second quote. Any Star Trek fans? I know there's at least one in the audience. Oh, good. So you've seen the M5 episode, right? The ultimate computer. That's the one where they decide to replace all the human crew on the starship, except for a few people. They put this brilliant artificial intelligence computer on there, and it's going to go prove that it's actually quite amazing and quite dangerous, and in some ways would make one hell of a weapon. just send that thing over into Romulan space and let it just blow the hell out of them, right? That was the right thing to do with that. But when they first kind of set it up, and it was kind of like, oh, I'm not sure this is the right thing to do, what did Captain Kirk say? There are some things that men must do in order to remain men. Pardon the sexist reference, but the series was made in the early 70s. Yeah, where are you on that question, right? Are there some things that men and women must do in order to remain men and women? Or actually, are we okay to let it go to the machines? The problem is, all of you who have the Captain Kirk mentality, you're hurting us, actually. If we're going to be like the AI folks and start making faster and faster and ever increasing amounts of progress, there are not some things that men must do in order to remain men. In fact, that's false. Right? However, popular culture and your artistic talents and your sentiments fight against you. So this is me too, right? I mean, I have the same dilemmas in me. So how about Seinfeld? Everybody watch Seinfeld? Anybody get the reference? All right, so there's an episode, one of the better Seinfeld episodes, I think, where George Costanza, kind of the perennial loser, right? He's unsuccessful at everything he does. And he has this amazing awakening that if every instinct he's ever had in life is wrong, well, maybe doing the opposite is a good strategy, right? So if our instinct to generalize, not specialize, if our instinct to pursue the romantic notions of superhuman effort overcoming the machines, right? Those instincts are wrong, right? Those are the wrong instincts. We've got to pull a George Costanza moment and do the opposite, which is you've all got to specialize in what you do, and you've all got to make the results of your specialties usable by other people. That's how we would create an industrial revolution in scientific computing. Not by having people like Fatmir just really dig deep into the guts of the machine and write the best possible finite difference code with his own single human effort. No, that's a disaster. That's 18th century thinking. All right, Fatmir knew this was coming. I warned him. Because every time he would come tell me, you've got to go learn CUDA, you're just, Fortran, piece of junk, get out of there, or C++, whatever. No, get in there and learn CUDA. And I'm like, oh God. Because I remember working on that connection machine where I could literally treat the machine as basically a direct implementation of the differential equation I wanted to solve. I wrote a little simple one there, right? And in 2 dimensions, it maps to a simple grid topology. But in fact, the machine could effectively appear to be any topology you wanted it to be, within some reasons. And I would always tell Fatmir, no, I'm going to show you this thing called the Getting Started in CM Fortran Manual, which was basically a thin little book about that thick, which basically had, I exaggerate, every single scientific algorithm ever written in 1 page in CM Fortran. How you do it, right? You want to do computational fluid dynamics? Here's a 1-pager. You want to do acoustic wave propagation? Here's a 1-pager. You want to do gravitational cosmology simulations? Here's a 1-pager, right? Just a thin little book that tells you how to do every scientific algorithm of importance. Right? It was an amazing thing to read because Danny Hillis had this idea of make the machine appear to be whatever you want it to be, right? Make it match the physics. I really love that. Now, Fatmir loaned me this book. This is actually Fatmir's book. If I'd shown you the page of the book, his initials are written on the side, right? I guess I need to give it back to him at some point. I haven't finished reading it yet, so can I keep it? Oh, okay, so I can keep it. Fantastic, I will. It is hard, right? It is hard to let go of that human element of this. But here's the real point. Go look at what your organization is capable of doing in terms of how much computing it can actually do. Is it seeing an exploding diversity of applications? Is it seeing accelerating value out of your investment in scientific and technical computing? If it's not, then it's stagnating. And if that's happening, you probably got to get some people to ask some different questions about what to do. Now, maybe some of it is kind of playing Seymour Cray, Danny Hillis, like crazy stuff, right? That occasionally really moves the needle a lot. But to make it sustainable, and here's the thing that personally I really find difficult to swallow. Probably got to act like software engineers, right? Really with that engineering mindset. We got to move all our mindsets down into that corner where we're looking at value. We don't care about the beauty of the object. The science we'll just accept as settled, and we're going to try to make something valuable by maximally leveraging other people's work. You want a singularity in scientific computing? You've got to leverage other people's work. I don't know. I wonder how many of the presentations will be like that today. Actually, there will be a few. I know there's a few of you that are going to kind of talk like that. So I think 2 things have to happen. Hardware has got to become more abstractable. So the more and more that you show me hardware that requires me to think very, very specifically about what the hardware's like, that's a disaster. That's going to detriment from this. Software's also got to become more abstractable. Well, the AI guys kind of figured that out, actually. Right? Painful as it will be for people like Fatmir, and me too in my day, to build their pride on their ability to write a faster piece of code than anybody else ever wrote for that problem. You know, to invent the quick sorts, right? Things like that. There's some evidence that we're doing some of that, but probably not nearly enough. Okay, with that, I'm happy to take your challenges. Questions too, but challenge is perfectly welcome. Dead silence. Okay. Yeah, please.
So if you
Use the mic, because I think they're recording it.
So if you don't do the programming today, okay, in a GPU, AMD, NVIDIA, whatever machine you want to use, who is going to do it for you?
Well, all right, so let's take that little piece of seismic recording instrument that I use. Right? I have to write a little bit of C++ code. Right? However, if you ask, how close to the metal is the C++ that I'm writing? It's not very. Right? It's kind of like the high-level architecture. Now, what it's calling is, it's calling probably about 3 layers of device drivers. Right? I have no idea what's going on in those device drivers. My wife, who's actually a much better programmer than me, she's probably dove down 1 or 1.5 layers into those device drivers. Right? Because one of the things I needed to do was to do asynchronous I/O. Right? I needed to be recording data and writing data to flash memory at the same time. Yeah, the device drivers they give you don't do that. Right? So she had to dive down and figure out how to do that. But actually below that is even more layers of things when you get all the way down to whatever that ARM Cortex M0 processor is doing, which I have no clue, right? I have no clue what that thing is doing. I just know that it does what I ask it to do. It's not that you know nothing. It's just that you do your very specific part. My specific part is I want to collect 5,000 samples in a row into a buffer. I want to check the time of the first sample and the time of the last sample and put that into a data structure and then stick that data structure on flash memory. Right? That's all the code I write, basically. But this thing is the equivalent of a 1970s multi-million-dollar seismic acquisition system because of the benefits of the Industrial Revolution. Because you can now fab all the components, in Asia for pennies, and somebody put all of that software stack on top of it, which I know next to nothing about, other than I have an interface to it, and the interface does what it says. Right? That's what it has to look like. In some ways, the connection machine was like that. I mean, if you actually said, I want to get down to the metal on the connection machine, oh God, don't ask that question, right? The original ones were single-bit processors, right? I mean, they weren't even multi-bit processors. They were single-bit processors. Still, there was a whole floating point arithmetic stack on top of it, which you need to know nothing about. I mean, ultimately, those of you who do down in the hardware metal stuff, you're probably at least working at the byte level, maybe at the bit level on some of this stuff. I don't want to know that. I just want to be able to stand on your shoulders. Actually, I want to stand on shoulders, on shoulders, on shoulders, on shoulders. Right? And as we get into more complicated things like a finite difference solver, why the hell are there so many finite difference solvers? Why do we all have to write one? Well, you write it because you're an artist, because yours is beautiful, you love it, right? Probably not because you're a scientist. You write it because you're an artist. Yeah, forget it. Artists have something to say in this conversation. I'm not saying they have nothing to say. But they can't dominate the conversation. Right now, we teach the artist to dominate, which is, my finite difference solver is beautiful. It's the one I like. I'm not willing to use anybody else's. Why? That's crazy talk. That fights against progress.
John, can I ask or paraphrase the question from Steve Poole?
Sure.
Are there things that we need to be doing over the next 5 years that we view as impossible? And how are we going to take that next big step that we're probably all a little scared to go challenge ourselves with?
What I'd love to see is somebody take another run at hardware architecture paradigms. Right? Because right now we're following the one which is just the massively exploding the number of instances of commodity, whatever the heck Intel and the other companies will provide. Now, I'm not throwing rocks against Intel. Their products are fine products, right? I think we're not dominating their thinking, though, right? They're not saying, I'm going to go design something which is really meant for scientific computing. No, they're trying to maximize their profits, which is fine. I'm a shareholder. I want them to do that. But they're not addressing us specifically, right? I would like to see somebody take a shot at something interesting in the hardware space that enabled this hierarchy of software stack to be built on top of it so that we can specialize in the thing we're interested in, right? If I need to take, I don't want to have to write a finite difference solver if fundamentally I just want to use the output of it. And not only that, I don't even want to write the thing that uses the output of it if what I want to do is use the output of that, right? I want to act like that Arduino developer community, where all I got to know is my last little piece in a simple abstract language. Right? So somebody's got to take a run at that. The problem is Fatmir's going to beat him the first time out. It's going to be like John Henry, right? John Henry's going to win that first race. The highly integrated, the thing that is potentially possible to have a singularity, will lose the first race. And we'll get discouraged. We'll be like, oh, well, no, I guess we're going to go back to the old way of doing things. I think somebody's got to try something different. That's my main answer to the question is somebody's got to try something different, because right now it just all looks homogeneous to me.
Well, thank you very much, John. Everybody, thank you.